So in the second of our series of 3 videos on sulfides, we're going to take a look at an example of boronite. So boronite has the ideal formula of Cu5, Fe, and S4, just one iron. So 5 coppers, 1 iron, and 4 sulfur atoms per formula unit. So let's say we have this composition that's given to us in weight percent. This is from mindat.org, so you can look this up. They say that a boronite could have about 25.55 weight percent sulfur. Copper by weight could be 63.38 weight percent, and then iron is 10.96. Well, if we had this kind of an analysis, could this really be boronite? Could it really be that stuff there? Well, we can make a check by looking at the atomic proportions or the mole proportions. Well, to get the mole proportions, so we'll write this mole proportion here, we would take the sulfur and divide it by its molecular weight, 32.065, that's in grams per mole. For copper, we divide it by this value here, 63.546, and then iron, 55.845. So these values in the numerator are in weight percent. We can call them grams if we like, doesn't matter what the units are, but if we let them be grams, that means if we had 100 grams, then 25.5 grams would be sulfur, etc. And then if we divide by grams per mole, the grams will cancel and the 1 over mole becomes moles. So the numbers we get here, these mole proportions, would be this. We'd get 0.797 for sulfur, 0.997 for copper, and then 0.196 for iron. That would be in moles. Now we'll call them a mole proportion because they do not sum to 1. They sum actually very close to 2, about 1.99. So if we want to turn the mole proportion into a mole fraction, it's supposed to be a fraction. F-R-A-C-T. Let's just leave it there. We'll divide all these by 1.99. 1.99, and then 1.99. This is called renormalization. Let's erase the chalkboard and give the answers. So we'll just rewrite the answer here. The sulfur value in a mole fraction would be 0.4003. For iron, it would be 0.50108. And then for, that is for copper. And then the iron value would be 0.0986. And now that should all sum to 1. So take a look at this. We said that the formula is Cu5 FeS4. How many atoms do we have here? Well, we have 5 coppers plus 1 iron plus 4 sulfur atoms gives us 10. And 4 out of those 10 are sulfur. So about 0.4 should be sulfur, and indeed it is. So far it checks out. In terms of the proportions of sulfur to the total number of cations, copper plus iron, it looks like we do indeed have boronite as opposed to, let's say, pyrite or some other kind of sulfide. So if we want to calculate the precise mineral formula, not just the general formula, the precise formula for this guy, we could simply take the sum of these two fellows here, and those sum to 0.5, right, 59968, and as they should, it's just 1 minus 0.403. So if we have let me write that again, 0.59968. That's the sum of copper plus iron. So now we could take 6. We have 6 atoms total, right? Copper plus iron, we need 5 coppers and 1 iron atom altogether. We'll just take 6 and multiply it by this over here for copper, 0.50108, and then divide it by the sum, 0.59968, so 0.59968. So for copper, we get a value of 5.013, very close to the 5 that we would expect. We could play the same game for iron. For iron, we would take this value, 0.0986. We expect 6 cations per formula unit, so we'll multiply that by 6 and then divide it by the total number of cations, which is again this number over here, 0.59968, and that gives us a value of 0.986. So the precise formula would be copper 5.013 and then iron 0.986 and then sulfur at just 4 cations. We're just assuming we have a perfect number of sulfurs. So this would be our precise formula unit, and that's pretty close to the ideal. So let's just rewrite that again. Our formula would be copper with a subscript of 5.013 and then iron with a subscript of 0.986, and we'll just say we have 4 sulfurs. So these sum to 6. And how close is it to ideal? Well, this 0.013 and this 0.986 are probably within rounding error and analytical error, close enough to call this a near perfect boronite of the original composition that we wrote, Cu5Fe(S4). So that's a way that we can check that we do indeed have a boronite, that we have the right number of sulfur atoms per number, the total number of cations, and then we can multiply these out to force the number to be 6, since we expect 6 cations here, to get a precise formula if we have something that is exhibiting solid solution and is a little more complex than what we've shown here, which we will look at an example of in the next video.